Good afternoon, morning, or evening. This will be day number 10. Let me move this here weird. Shrink it down here. Get that out of on the other side. Kind of does some weird stuff there. That's the screencastify that I used to record. Has changed updated their stuff, and it always pops up on the same screen now. But that's okay. So what we're going to do today in physics is we're going to be looking at gravitation, and we're going to be looking at an application of universal gravitation, orbital periods, and satellites for planets and satellites. I was going to do Kepler's laws, but I don't think we need to bother with Kepler's laws. It's got some pretty interesting math in them. If we have time, maybe we'll get into Kepler's laws later. We'll see. But we'll look at orbital periods today for planets and things like that. As soon as this thing opens up here, just waiting. There we go. Okay, so let's get this set up. Just shrink this down a little bit. Sorry guys, I'm just setting up on the other side here so that I can actually see what I'm doing. Okay, so what are we going to do today? Hey, this is day 10 in the fields unit. The third one. And we're going to be looking at an application of universal gravitation. We're going to be looking at orbital periods and speeds. That's what we're going to be looking at. We're going to be looking at that. And the way I have to start this is I have to go through centripetal acceleration or circular acceleration. I know that circles, the planet is not a perfect circle. Sorry. And all that kind of stuff, but we're going to use, it's pretty close to being a circle, so we're going to use that as an approximation, and that's so that everything's not going to be exactly perfect. There are elliptical orbits of planets and satellites orbiting around the Earth. The Earth is not a complete perfect sphere and all that kind of stuff, but these equations do make good approximations. So the first thing we've got to do is we've got to look at centripetal acceleration. Centripetal doesn't have two A's in it. It's got an E there. Okay, and that's what we're going to apply first. So if we have an object in a circular motion, let's kind of get this off the ground by drawing the circle here first. Okay, so if I have a circular motion of an object, so let's say that I have so I have an object going in a circular motion with some radius r, and it's going around in a circular path, and it has some velocity on the outside of the circular path. Okay, so this is objects in circular motion. Okay, and if it's going at that velocity, that edge velocity, the acceleration in a circle, which we'll call AC, equals the velocity squared of that object over the radius. So this is the acceleration in the circle. This is the velocity of the object. In meters per second. Okay, this is the radius of the circle. In meters. So obviously you're going to get meters squared second squared divided by meters, so you'll get meters per second squared, which is an acceleration. Okay? Okay, so we're going to need that for when we get into motion, planetary motions, and things like that. So let's do a quick sample of centripetal acceleration, just to show you how it works. Okay? Say a car is moving 30 meters a second and travels through a curve. It travels through a curve with a radius of 25 meters. Here. Find the acceleration of the car in the circle, or in the curve, I guess is a better word, even though it's a circle, right? And period, what force would a 65 kilogram person feel as they travel in the car, as they go around the curve? Okay, so if we look at this question, we can apply the acceleration part of it. Okay, so first of all, let's find the acceleration in the curve. So the acceleration in the curve is going to be equal to 30 meters a second squared divided by the radius of 25 meters. Okay, so if we work that one out, we get uh, 0.0. And one of the meters is going to cancel out. So if we do the calculations for that one, 30 squared divided by 25, we get 36 meters a second squared. Which is quite a lot when you think about it. So if we think that G equals 9.8 meters per second squared, and we go 36.0 over 9.8, That would be 3.67 Gs. So this person in the circle is experiencing 3.67 Gs of force. Or we could do it like this. We could say force equals mass times acceleration. And we could say the 65 kilogram person would be experiencing so many newtons of force, which would be 36 times 65, 2,340 newtons of force in that circle. But an easier way to understand it is how many G's are going. 3.6 G's is a lot of G's to go around a circle in, right? Okay, so that's a typical acceleration type question. The reason we need this acceleration is because later in the, or we're going to be looking at planetary motions. That in planetary motion, we're going to look at circular motion. Okay, a satellite orbiting around the Earth in a geosynchronous orbit. What's the period? Okay, and what's the velocity of the satellite, depending on how high above the Earth it is, and this kind of stuff. Okay, and that's all applications of universal gravitational theory. So that's just, we're going to need that equation to help us out in our next step, which our next step here is to derive this. So let's do orbits of satellites. Let's do that next. So we're going to need this plus a bit more information. Okay, so in this part here, we're going to look at finding an equation for the velocity of a satellite in orbit. So if we kind of figure out what we're going to do here, we're just going to derive it. So this is the derivation first. Not calculus derivation, just deriving it out of basic equations. So let's draw a picture so we can see it. Again, we're going to be using circles. So let's draw an Earth, and let's draw, okay, that's supposed to be centered, but it's not perfect. But, and let's draw a satellite. So let's say that we have, let's use a different color here. Okay, so there's the center of the circle. And let's say that this is our satellite in orbit. Okay, and this is my planet here. Okay, and we know that this satellite has some velocity. Okay, so we want to derive it. So first thing we know is that this acceleration due to centripetal motion is v squared over r. Okay, and this is the velocity of the satellite to stay in orbit. Oh, I keep not putting enough L's in satellite there. Let's do that properly. Okay, so that you have to be going fast enough so that you stay in the orbit and you don't decay down to the earth. So that the gravitational force has to equal the centripetal force outward. And if they're balanced, then you'll stay in orbit. If there's more gravitational force, it'll pull you back into the earth and your orbit will decay. Okay, so Newton's second law, Newton's force law, if you like. Okay, F equals ma. So F centripetal equals mass of the satellite times this acceleration, which is v squared over r. Okay, and this is a circular force outward, and this is the mass of the satellite. Okay, and then everything else we know, that's the velocity of the satellite and the radius that it is. Okay, and this has to equal the force of gravity. Okay, so force of gravity pulling the satellite down, so there's this FC perpendicular out, and then there's an FG force of gravity. Now we know the force of gravity equals the mass of the satellite. I guess we should put gravitational constant first. It's the gravitation, Newton's law. It's the gravitational constant, which we called G, capital G. It's going to put K in there for Coulomb's constant. It's capital G, the gravitational constant, times the mass of the planet, times the mass of the satellite, divided by the radius, squared. So this is the mass of the planet. Mass of the satellite, universal gravitation. This is the force of gravity. Okay, so by theory, to keep your orbit, the force of gravity has to equal the force of centripetal acceleration, or force in a circle. So if we can equal those two equations together, we can come up with an equation and solve for the velocity. So we know how fast that satellite has to go. Okay, so if we take our force of gravity, G, times mass of the planet, times mass of the satellite, divided by r squared, that's going to equal the gravitational force, which was ms v squared r. Okay, now we can see that there's some things on both sides that are the same. Okay, so if we cancel an r from the bottom, and we can cancel the mass of the satellite, okay, the mass of the satellite doesn't matter. It's good. Okay, so now we have an equation for the expression v squared. So therefore, v squared equals gravitational constant times the mass of the planet, okay, divided by the radius of the orbit. So we have to kind of get v, so we have to square root that. So it's the square root of gravitational constant, mass of the planet, over the radius. Okay, and that's all under the square root sign. And this is the velocity of the satellite needed to stay in orbit. And that is one of the equations right there. Okay, we know that that's the gravitational constant That's the mass of the planet, and that's the radius of the orbit. Okay, you won't have to derive this, because you'll get the equation. And there we go. Okay, this is in whatever the units are. Mass has to be in kilograms. Radius has to be in meters. Okay, let's move that up so that it's not behind my head. Okay, and that is our first equation that deals with finding or deriving that. I'm going to look at the clock here for a minute. Okay, what we'll do is maybe we'll derive the orbital one as well. And then if we have time, we'll do some examples after that. If not, we'll do the examples the next day. So let's go ahead and derive periods of the orbit next. So that gives us the velocity of the orbit of the satellite. So the next thing we're going to do is we're going to try to derive the period of the orbit. Okay, so finding the period of the orbit. I'm going to do that on the next page. Okay, so finding the period satellite. I keep spelling that wrong. Okay, and this is we're gonna have to kind of look back on the centripetal acceleration from Kepler's law. So I'll have to give you Kepler's law as well. We don't really want to go into where it comes from and how, but I'll just give it to you as the acceleration of Kepler's law. Let me just find it here first of all. So let me pause for a second and find it first so that we have it in front of us. All right, so I looked around a bit and decided that the derivation of this one's a bit more complex. It has some geometry in it, but anyways, just to give you an idea, the acceleration in orbit can be written in a circle. Okay, we've got v squared over r okay, and this, if you break it down into some geometry of spheres and so forth, you can say that AC is equal to 4 pi squared r over t squared. Okay, and this is basically a geometric equation that is equal to this, where t is the period of the satellite. Okay, now that's what we're going to use. But if we equal that to universal gravitation, if we say that and we work it out, we can calculate that t for any period of any satellite around a planet is equal to 2 pi square root, I'm not going to derive this, I'm just going to give it to you, r cubed, and that comes from Kepler's laws, g mp, the mass of the planet, which usually is Earth. Okay, so this is our period. So this is the period of the satellite. of orbiting object, because it could be the moon too, right? This is the radius of the orbit. So don't worry about these two, but basically that one there, that's just some geometry. So this is the one we're going to be using. This is going to be the mass of the planet. And this is the universal gravitation constant. Okay, so that has its own units. This is going to be in meters. This is going to be in kilograms. And this ends up being in seconds here. Okay, and you're like, well, how does that work when you don't even have a velocity in there? Okay, well, when you think of it, it'll give you the period of the orbit. Basically means how long it takes the thing to go around once. Okay, and there's newtons in the universal gravitational constant, so that newtons has a meters per second squared. So that's where you end up getting your seconds from, is that newtons part. Okay, that comes out of the universal gravitational constant, and that's how it ends up being this way. So that's the universal gravitational um, period. So if we look at doing an example or two of these using these two equations, the period equation there on this page and the velocity equation on this page. Okay, so let's kind of look at it. We'll do a couple examples of that, or maybe one example. We'll see how far we can get today of doing those. So let me just um, get it set up there. There we go. There, I'm just setting up some examples. Okay, so time-wise, we can do maybe one or two examples of this. Yeah, two examples we'll kind of go through here. So let's say that we have, okay, so digging one up here about a satellite going around the Earth. So, okay, so a satellite orbits I keep on putting an I in there. The Earth at 220 kilometers above the surface. Um, Given that the mass of the Earth look it up, but I've got it here in my book here, is 5.97 times 10 to the 24 kilograms. And the radius of the Earth, or does it say diameter? It says radius. Don't get mixed up between those two. Is 6.38 times 10 to the 6 meters. What is a satellite's orbital speed and period? Okay, so we first should fix these as scientific notations. Okay, notice that kilometers is there and meters is here, so we're going to have to convert things to the same unit. Okay, so basically all our givens are there. Now, if we're thinking about this problem, okay, we have to get the total radius. We don't want just the radius of the Earth. So the radius is going to equal the radius of the Earth plus the height of the satellite. So that's going to end up being, if we take this, it's going to end up being radius of the Earth is 6.38 times 10 to the 6 meters, plus, if we write this in meters, it's 2, 0, and then 1,000 more. 1, 2, 3 meters, which equals, if we do that on our calculator, carefully, making sure that we use proper scientific notation. You get 6.6. 0, because it's 3 significant figures, times 10 to the 6 meters. And that's the radius, the total radius. Okay, and now we know the mass of the Earth. Okay, and so we can use that information now to calculate our orbital period and velocity. Okay, so let's go and do the one that we just did here. Let's use this one to get our period. So it's r cubed over g m. Okay, so let's do the period. Okay, it's 2 pi r cubed over g mass of the Earth. Put a little e there for Earth. Okay, so that would be 2 pi square root of radius 6.60 times 10 to the 6th meters cubed over 6.67 times 10 to the negative 11, which is our constant of Newton meters squared seconds squared, times the mass of the planet here, which was 5.97 times 10 to the 24 kilograms. Okay, so that's going to give us our period. So 2 pi. Okay, let's do the cube part, write it out, and let's do the bottom part, write it out. Okay, so 6.6 exponent 6. Oh, that's kind of creepy. Cubed. So to the power of 3. Looks like this on my calculator. Okay, hit that one. You get 2.874. I'm not going to round anything off here till the end because we're dealing with big numbers. Okay, and then we're going to multiply these two together. 6.67 exponent negative 11 times 5.97. Scientific notation. What is it? 24. 3.98199 times 10 to the 14. Okay, continuing on with our number crunching. T equals, okay, we're going to divide those two out. 2 pi square root of this division, so I'm not going to 2.87496 scientific notation 20 divided by 3.98199 scientific notation 14. Okay, so I got 72191, rounding off a little bit there. Okay, now we square root that. So we get t equals 2 pi times 849.7. Okay, and I'm keeping it on my calculator as I do this. Times 2 times pi, which I have a pi button on my calculator. And I get 5, the period is 5,300, we'll go to the nearest second, and 39 seconds. Okay, so if we look at that, that's about 3,600 seconds an hour divided by 3,600. It's approximately 1.5 hours. Okay. Now let's do the velocity one. Okay, so I'm going to do the velocity one on the next page, I think. Yes, I'm going to do it on the next page. Okay, I just got to respond to an email real quick here that just popped up. So I'm just going to pause here for a second, and then we'll do the last calculation, and then I'll be it for today. Okay, just finishing up. Okay, this is our velocity equation. Square root of gravitational constant times the mass of the planet over the radius. Okay, so if we remember our numbers, okay, G is 6.67 times 10 to the negative 11 times the mass of the planet, 5.97 times 10 to the 24 over the radius of the planet, which was 6.6 times 10 to the 6th, square root of. Okay, take your calculator out. Okay, 6.67, scientific notation, negative 11, times 5.97, scientific notation, 24. Okay. Divided by 6.6, scientific notation, 6, square root. Okay, so I guess we'll go with 3 significant figures here. So 7,770 meters per second is that orbital velocity, which is a fairly fast if you think about it. So that's pretty good orbital velocity. Oops, let me get that pen out of there. Okay, so I think we're going to stop there today. We've gone into about 40 minutes, which is kind of long. So we'll stop there, and maybe tomorrow we'll talk about gravitational fields and apply gravitational field to it as well, and maybe do a couple more examples, some more practical type problems as well. Okay, so we'll see you tomorrow.